Welcome to EDU World Space.
To find the maximum electrical force that these protons will exert on each other, we need to first find out the work done to bring the protons against the electrostatic repulsion from one configuration to another configuration, and it's stored in the form of electrostatic potential energy. So from the law of energy conservation, potential energy is converted into kinetic energy. The potential energy equation of the system of the two charged particles is this. Hold on, let me just write down the equation for the potential energy of these two charged particles. So it's over 1 over 4 pi E0, which I will explain in a bit, times, so this is all over 1, times the first charge, the second charge over the radius, or the distance between the two molecules. So this is actually Coulomb's constant, and in this case, the permittivity is the permittivity of free space, so therefore it is constant. So using the energy conservation to find the closest approach between the protons, initially the two protons are several meters away from each other, so the initial electrical potential energy Ui of the system is 0, so the initial, this is important, so the initial potential energy of the system is 0, and the initial kinetic energy of the system is, so let's get that down, Ki is equal to 2 times 1/2 mv squared. So in this case, it's the mass of the proton and the velocity of the proton. And so the distance, so now we can simplify this. Let's actually just simplify this expression a little bit first. So we can cancel out the 2's here, and it'll just be mv squared. That's the initial kinetic energy of the system. So the distance at which the electrical force will be maximum is when the final kinetic energy of the system becomes 0. So when Kf becomes 0, then that will be the distance at which the electrical force will be maximum. So let's assume that r is the distance between the two protons in the final position, and so in this final position, this is where the final kinetic energy is 0. So let's just call that distance r, and let's put this into our, so the distance will be r, so let's use the potential energy equation. So the final UF is equal to 1 over 4 pi, so this is just Coulomb's constant, the permittivity of the medium, times the two charges of the electrons, and since they're opposing each other, one will be a negative charge and one will be a positive charge, so it's times positive charge electron over the radius. So this is the distance, which I said we're going to just call this r for now. Yep. So according to the conservation of energy, the total energy, initial energy of the system is equal to the total final energy of the system. So to put that into writing, so the K, so let's get that over here. So this is just a conservation of energy law. So the Ki plus potential energy, initial potential energy, is equal to, theoretically, in ideal scenario, in ideal conditions, is equal to the final kinetic energy plus the final potential energy. This is just an expression for the conservation of energy law. This means that no energy is being lost. So now if we substitute the values for kinetic energy here, into this equation. So if we do that, we're going to get that and the values of the potential energy. So in this case, we know that the initial potential energy is 0. So on this side, it'll just be the initial kinetic energy, which we said is equal to mv squared on this side, and it's equal to the final kinetic energy, which is 0, because we know that at this distance the kinetic energy is completely 0, so it's just the potential energy. So it's just this. So it's the other side of the equation. So now if you substitute all the values for this, for the Coulomb's constant and the charges of the electrons, we're going to get that the radius. So let me just first isolate the variables before plugging anything in. So if you move this over here, so let's just call this constant K. So K, and when you multiply these, it just becomes electron squared. No, it does not become negative electron squared. It just becomes electron times negative electron times a positive electron over the radius. So if we solve for this radius, we just need to cross multiply this expression, and we can isolate the variable r. So these are actually two different. This is velocity and this is the radius. So this is the r. If you are unclear, let me just redo that. So this is actually r. Yes, that's a better r. So now it's just going to be k times the 2 electrons over mv squared. Hold on, let me do the division sign a little bit better. So here we go, over mv squared. And if you plug in all the values, we get that r is equal to 9 times 10 to the power of 9 times 1.6 charges for the electrons, 1019 to the power of negative 19 squared. So this whole thing is squared because there are 2 electrons, and we can just square it when we multiply them together over the mass of the 2 protons, which is 1.67 times 10 to the negative 27 kg. Just keep them in standard units, so it'll be easier for us to know the units at the last step of the problem. And we already know that the final speed is 1,000 kilometers. And to just turn this into standard notation, let's just multiply this expression by 10 to the power of 3 to make it into meters per second instead of kilometers. And that's it. Now, if you put this into our calculator, we're going to find out that the radius is 1.38 times 10 to the power of negative 13 meters. That's why we kept it in standard units. So now we know the units. So now the maximum electric force between the 2 protons is, if you use this equation, let's move on to the second part. So let's use a different color. So this is an important value that we'll be using for this equation to find out the maximum electric force. So F max is equal to K, which is that, remember, that we stated this before, so we don't need to say it again, times electron squared over the radius. So now that we know the radius, we can just plug that in. So this will be 9 times 10 to the power of 9 times the charge of an electron, which is 1.6 times 10 to the negative 11 squared over the radius. Sorry, there's actually squared over here. Over the radius squared. I knew that was missing something. So 1.38 times 10 to the power 13, and this whole thing squared. So now if you plug this into our calculator, we're going to find out the maximum electric force between the two protons, which is equal to 1.2 times 10 to the negative 20 newtons. And this is the maximum force.